Hello everyone, welcome to another video of quantum field theory. In today's video, we'll be finishing up our calculation on the Casimir effect. So from our video on Noether's theorem, we found an expression for the Hamiltonian, where the Hamiltonian was the integral of the T naught component of the stress energy tensor. And if we were to plug in our fields, we'd find out that this is simply another way to write out the Hamiltonian. And this is analogous to what we did in the third video, where we wrote out the momentum operator in terms of the creation and the annihilation operators. And through some logical reasoning, we can find out that this Hamiltonian is going to be equal to this right over here by using the same steps that we used for the momentum operator. And like before, the second term will diverge to infinity, which implies that our Hamiltonian is actually infinite, meaning that all energies of our quantum systems are also infinite, including the vacuum state, which is obviously a problem. So usually we artificially remove this divergent term, and some of the reasoning here is that only the differences in energy are actually observable. And by removing the divergent term, we get this Hamiltonian right over here. So this is the exact same reasoning that we used for the momentum operator, which was we covered that in I think the third video, one of those videos on second quantization. We covered the momentum operator. It's the exact same steps for the Hamiltonian instead. And the Hamiltonian is going to actually act on some quantum state and give us the energy that is contained in that state. And we can also prove these relations right over here by simply explicitly calculating those commutators. And these are important commutators that we will use in the direct future. So a question that we can ask is, what happens to the energy when we add more particles in our system? You guys probably know the answer. The energy should increase in our system. And by the way, we are using our modified Hamiltonian here, where there is zero vacuum energy. So to find out the answer, we can just multiply our Hamiltonian by the creation operator acting on some entry agent state, but actually we are instead going to use the annihilation operator for now. So by doing that and doing some more math stuff, we will find that this over here is just equal to this over here, and by doing more algebra and stuff, we will find out that when our annihilation operator acts on some energy agent state, it will lower the energy by omega k prime. So not only does A of k destroy particles, but it also lowers the energy of the system by the square root of k squared plus m squared. And this makes logical sense, right? So for those that may not be following right now, all we're saying here is that each particle in our system contains an energy of k squared plus m squared, or the square root of that, which is also known as omega k, right? So if we remove one particle in our system, that just means that the energy of our system decreases by the square root of k squared plus m squared. So if we have three particles in our system, our total energy is just going to be 3 times the square root of k squared plus m squared. If you have 2 particles in our system, the energy is going to be 3 times k squared plus m squared minus k squared plus m squared, which will just, of course, give us 2 times k squared plus m squared. That's all we're saying. So this makes intuitive logical sense. So what happens when we add a particle in our system? Well, using the same reasoning, we can find out that when we add a particle in our system, the energy will increase by omega k prime, which also makes sense. So if our energy agent state turns out to be the vacuum state, that means that A conjugate acting on the vacuum state will have an energy of the energy of the vacuum state plus omega k. But since E naught is formally infinite with the original Hamiltonian, that new state will also have an infinite energy. But working with the modified Hamiltonian, that new state will just simply have an energy of omega k if the vacuum state's energy is 0. And we can generalize this a bit. If the Hamiltonian acts on this state, which has n particles with momentum k and m with k prime, we will get a new state that has the vacuum energy plus n omega k plus m omega k prime. So this so far is making, or at least should make, at least some intuitive sense. I was going to make a video covering just this content, but I thought that it would be like too like sort of redundant because it's exactly the exact same steps from our momentum operator video. So if anything here doesn't make sense, just watch that video on the momentum operator and things might be more clear. So with all this background, we are finally able to derive the Casimir effect. And let's do that now. So the Casimir effect essentially relies upon the concept of that 0-point vacuum energy. And like we've talked about previously, the existence of 0-point energy is usually taken to be 0 when we are doing calculations in quantum field theory. However, there is an argument against us pretending that infinite term doesn't exist, but that argument is the Casimir effect essentially. So basically, to derive this Casimir effect, we're going to treat that 0-point energy as being a non-zero value and to see what follows from there. And we are going to work with 1 + 1 dimensional space-time to make our analysis much more simpler. So remember from our part 1 video, in the Casimir effect, we have two metallic plates, and they are each situated at x = 0 and x = a. And the point of these plates is that the fields go to 0 at the plates. So if you have some sort of quantum field here, it has to become 0 at those plates. And that is going to imply that our free scalar field looks like this over here. And the fact that we have those boundary conditions makes our momenta quantized. There are momentum k equals n pi over a, where n is some integer value. Now we are going to assume that we have only a positive momentum here. We don't want to consider fields with negative momentum. We are only considering fields with positive momentum in this analysis. So basically, n is just going to be an integer but positive, so a counting number. So we get this formula for our energy. Our energy is now quantized, so is our momentum. And yeah, that's where we kind of left off in the first video on the Casimir effect. So now what we have to do here is apply these concepts but to the Hamiltonian now. So you know that here is our Hamiltonian in general for a free real scalar field. And by multiplying the Hamiltonian by the vacuum state, we get this over here, because this is just the number operator, right? And when that acts on the vacuum state, we get 0. So we are going to get this over here, which implies that the vacuum energy is 1/2 times the integral of this divergence thing. And like we've said before, this is going to be equal to infinity. And yeah, that's a pretty big problem, but let's see if we can sort of try to treat this infinity. We know that the delta function is just the integral over position and over 2 pi e to the minus I kx. That should be delta k, right? This is the delta function in one dimension. This means that delta of 0 is going to be the integral of dx over 2 pi times e to the minus I k times 0, and that's just going to be 1. So usually we'd be integrating over all of space, but instead what we are going to do is integrated over some finite volume, like say alpha or like minus alpha to alpha. Therefore, this entire integral just comes down to being equal to 1 over 2 pi times integral from minus alpha to alpha of dx. And that's going to give us just some finite volume. We're going to call that volume V, which is just going to be equal to alpha plus alpha, so just 2 alpha. But we're just going to call that V as a shorthand. So this is going to end up giving us V over 2 pi. So yeah, that's how we kind of remove that infinity there. But what we can also do is sort of absorb the 2 pi into this volume V and then have like a V prime, right? So yeah, and also something that's important, this should not be the 3 volume element over 2 pi cubed. It should just be dk over 2 pi, since we are working in 2-dimensional space-time. That's an important thing that I should have addressed. This should be dk over here. This should also be dk. And this should be dk as well. So yeah, so with this over here, this term over here just becomes some volume v prime. And that's how we can kind of get rid of that delta function by just using the property of the, just using property of where a delta function is equal to the integral of those plane waves, and then taking a finite volume, and then, yeah. So we've made the expression finite now, but there's still a problem. The volume V is going to be inside of our calculations. No, if you want to be general, we don't want a volume V to be left in our calculations. So you want to remove that volume V. So to remove the volume V, we can consider taking the energy density, or just looking at the energy density, E naught over V prime, instead of looking at the energy itself. Because our energy will depend on our volume, right? If we have a larger volume, we'll have more energy. But we don't want to make a prediction that depends on a specific volume, right? Because it will only apply to just that volume. We want to be more general. So instead, we want to look at the energy density, which is just E naught over that volume, the energy per volume. And that will make the V prime drop out of our calculations, if that makes sense. So E naught is going to be V prime over 2 integral of dk omega k, right? So then E naught over V prime is just V prime over 2 V prime integral of dk omega k. And that just gives us 1 over 2 times integral of dk omega k. So yeah, that's E naught over V prime. Most textbooks will write this, at least the one that I looked at, they'll write this as epsilon naught for the energy density. But by abusing notation, we are still going to write this out as capital E naught, just because I'm used to it, honestly. But we should be writing this as like a different letter. So just whenever I write E naught from now on, I mean the energy density. So with that being said, yeah, that's the main setup that we are using here. So what do we do now? Well, now we can note that omega k is the square root of k squared plus m squared. And again, k equals n pi over a. So that means that omega k equals the square root of n squared pi squared over a squared plus m squared. Now, right now, we are working with a scalar field, right? But in actual real life, the field that we should be considering here should be the electromagnetic field. Now, what's the reason for this? Well, the reason is that the plates that we have here are actually metallic, right? And metals are described by electromagnetism, right? Because like that's their whole like gist. So it's their whole shtick, like E and M, right? So we should be considering the electromagnetic field here instead of the scalar field. Like the only real life application of the scalar field that we know of so far is the Higgs field, and to approximate some other fields. So for a real life scenario, we should be dealing with the EM field. Now to describe the EM field, we have to make a few modifications. First of all, we need to note that a actual photon field is massless, right? So this M term just drops out to being 0. So this means that omega k now becomes the square root of n squared pi squared over a squared, which is just n pi over a. So that makes this expression much more simpler, much more easier to work with. So now we have that E naught is going to be 1 over 2 times the integral of dk omega k, right? And since omega k is n pi over a, we really now have 1 over 2 times the integral over actually wait. Not so fast. We don't want to integrate just yet. We have an integral, yeah, but remember, since our fields are quantized, right? Since n is going to be a counting number, basically, this integral is going to turn into a sum over k. Where we have square root of k squared, basically, plus m squared, but then m is just 0. And since k is n pi over a, we just have a sum over k, or really a sum over n. Then we have n pi over a. So basically, we had an integral over dk, right? But the integral turns into a sum over n, since k is quantized and the free parameter in k is going to be n. So our sum turns into an integral when we have a discrete summation, and then omega k is just going to be n pi over a, since we have a massless field. So now we can just move the pi over a to the front, since that's just a constant. We have pi over 2a times the sum over n. So yeah, or we should really say the sum over n equals 1, since we start at 1. So that's what E naught is going to be. And this is the energy density inside of our plates, where the fields are quantized. Now there's actually one more modification that we need to fully describe a photon field here. You know that photons have two linearly independent polarization states. So we should actually sum over those polarization states as well. So we should have a sum from nu equals 1 to 2, and then n equals 1, and pi over 2a. So we should be summing over those polarization states. So when we do that, that just gives us n pi over 2a plus n pi over 2a. So here's for the first polarization, and then here's for the second polarization. And that's just going to give us 2n pi over 2a. The 2's cancel out, and we just have n pi over a. So essentially, we had to make two modifications to describe the EM field. The first modification is to let the mass be 0. Second is to sum over the polarizations. So by doing that, we just have that E naught, the energy density, is just a sum over n equals 1. We can, again, take out the pi over a to the front, and then just n. So here's the energy density inside of the plates for a photon field. So our energy density inside of our plates is going to be this summation over here. Now this energy density is still actually divergent, because this is just going to be pi over a times 1 plus 2 plus 3 plus 4, and so on, which is still infinity. So even after using a finite space-time volume, even after using a summation instead of a continuous integral, we still have a divergence for our energy density. But just for fun, just to humor ourselves, let's keep going to find the energy density outside of our plates. So outside of our plates, by doing the exact same thing, we're going to have that the energy density is going to be the integral over dk times, or integral over dk k. It's a bit clearer to see if the dk is at the end of the integral, where we are integrating over all positive values of k. So that's just from 0, or really from 1 to infinity. Or actually, we can just integrate from 0 to infinity, just for funsies, if you want to consider the case where it has 0 momentum. So yeah, that is what E naught is going to be. And it turns out that we can actually write E naught sort of like this over here. Now, first of all, we have a continuous sum, basically, which is just an integral, because outside of our plates there is no quantization, right? So that's why we have this integral over here. Now we can write k as being n pi over a, even for outside of the plates, right? Because since k can be any number we want, that means that n can be any number that we want. So for example, if we want k to be 1,000, well then that just means that n is going to be a times 1,000 over pi. So we can still write k equals n pi over a, even if k is not quantized, as long as n is not quantized either. So we can still actually write this integral as being the integral from 0 to infinity, then moving that pi to the front, and then now it's going to be an integral over n instead. So yeah, so these two mathematical expressions look very similar to each other. In fact, they are actually the same. The only difference is that we have an integral instead of a discrete sum for outside of the plates. So for inside of the plates, we can only have certain energy values, but outside of these plates, we can have any energies that we want to. Now, we can actually look at the difference between the energy density outside of the plates, or actually the difference between the energy density inside of the plates with the energy density outside of the plates. Because it turns out that there's actually going to be a difference. Well, it won't make sense now since these are both divergent, right? But once we regularize blah 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 this thing, which will make sense later, we can take the difference between these two energies, and there's actually going to be a non-zero difference between the 0 point energies, which will cause there to be an attraction between the plates. Right now that's nonsense, since infinity minus infinity is like, doesn't make any sense, but it's going to make sense down the line. So you want to subtract the inside energy from the outside energy. We're going to call that delta E for the change in the energy. And that change in the energy is, of course, going to be equal to pi over A times the sum over n to infinity, of course, but we're going to just drop that out, minus the integral from 0 to infinity n dn. So yeah, that's what the change in the energy is going to be. But of course, these are both infinity, so like it doesn't make any sense, right? But there is something that we can do to kind of put some sense into this expression. Now we know that the limit as epsilon approaches 0 for e to the minus epsilon x is going to be 1, right? Since e to the 0 is just 1. So what we could do is a very sneaky trick we can say that delta E is just pi over A times the limits as epsilon approaches 0 for this sum, n e to the minus epsilon n, right? So we're going to use n instead of x this time, minus the limit as epsilon approaches 0 times the integral of n e to the minus epsilon n dn. So again, all we're doing here is we're just multiplying the inside terms by just 1. That's all we're doing. Where 1 is just the limit as epsilon approaches 0, e to the minus epsilon n. Why are we doing this? You'll see shortly. So now what we can do is we can just factor out this limit away from here, giving us the limit as epsilon approaches 0 of pi over a times the limit, we already did that, times the sum from n equals 1, n e to the epsilon, or minus epsilon n, minus the integral from 0 to, when I say n, it should be from 0 to infinity, my bad, to infinity. Let's move this to the left a bit because it's getting a bit clustered here. N e to the epsilon minus epsilon n dn. So we now have this right over here for the change in the energy densities. So yeah, this should be the same expression, but why are we doing this? Why are we like putting this e to minus epsilon n term here? Well, there is a physical interpretation of this. So e to the minus epsilon n, right? If you were to graph it, you're going to get something that looks like this. It decays as n approaches infinity, right? And we have to think about what we really have here. We have two plates here, right? And this is where the second interpretation of the Casimir effect kind of kicks in. This might sound very strange, but we have a photon field, right? And basically, if we have real metallic plates, right? In real life, metallic plates aren't like rigid, right? Like they're not like impenetrable, right? So for high enough photon fields, they should leak out of that metal wall. That's how we have it set up here, right? Is that the fields go to 0 at the plates and they can't like pass through. But in real life, we can have photon fields with enough energy that they can sort of like leak through the plates. And we aren't accounting for that leakage if we treat the metallic plates as like impenetrable, right? So the reason why we have this e to the minus epsilon n here is that for n approaches infinity, right, which just corresponds to us having a high enough momenta, since remember that the momentum is just n pi over a, so it's n approaches infinity, k approaches infinity. So this just means that if we have high enough momenta, this term is going to 0, meaning that we aren't factoring in the fields that leave the plates. We shouldn't factor in the fields that leave the plate. So for higher and higher frequencies, it should go to 0 since we don't want to count those fields. So that's sort of the physical interpretation of this e to the minus epsilon n, right? But then there's of course a more kind of mathematical interpretation where 1 is literally just a limit as epsilon approaches 0 for e to the minus epsilon n. But that's the interpretation of adding that like sort of a decay factor there. And it turns out that by adding this factor over here, it's going to make this finite. And the reason is that this expression that we had right over, no, not here. Yeah, this one right over here was technically speaking wrong. Because again, we weren't factoring in that the photon fields can escape those metallic plates. So by making this step over here, we aren't being rigorous mathematically. However, if we say that, oh, well, these metallic plates should like have some leakage going on by that exponential factor, then we have the right expression, and then we can take that limits out right there to get a finite expression. If that doesn't make much sense now, it's fine. I didn't really get that at first. I still kind of don't, but it after some amount of time of thinking about it, it makes a little bit more sense. So that's why we add that dampening term there. But then again, you can think of it as like a trick, a math trick, if you want. So yeah, we now have this expression right over here. I spent a bit of time talking about that interpretation because it's a pretty big part of the Casimir effect. That's why I took a bit of time to sort of explain that thing. But yeah, now we have this over here, and you guys can notice that this over here and this over here, these are very similar expressions. They're exactly the same, except that instead of a summation, we have an integral. Now, there's actually a formula in math called the Euler-Maclaurin formula, right, or whatever it's called. Oops, ignore the bottom part. There's a formula in math called the Euler-Maclaurin formula. And I have it conveniently placed underneath here. And it essentially relates the difference between a sum and an integral. So an integral with a closely related sum. So if you want to find the sum from like 1 or from I equals 1, where we have I squared plus 1, minus the integral from 1 to 3, so it goes to 3, of x squared plus 1 dx, or I should probably just say I squared plus 1 di. So we have I squared plus 1 di. To find this difference, we can use this formula right over here. So the Euler-Maclaurin formula relates the difference between a summation and a closely related integral. So we have a sum from I equals a to b. I should put that here. We have from I equals a to b of f of I minus the integral of that. So we can actually apply this neat formula from math to actually solve this expression right over here. Because it turns out that our function in this case, our f of I, could just be e to the, or actually it can just be n, e to the minus epsilon n. And we have a sum minus an integral. So yeah, we can just apply this formula. So in this, for our case over here, the a would just be 1 since we start at 1. And the b would be infinity since we go up to infinity. So this is where the math gets a bit messy, so I might lose you guys. So for the sake of trying to be as clear as possible, I'm going to try to sort of break this down into multiple parts. But just a warning, it might get a bit messy. So let's try and do that. So what we are going to do here is we want to focus on the inside term where we subtract the sum with the integral. First of all, we can't really apply the Euler formula just yet because you can see here that we have I equals a and we start at a. But here we have n equals 1, but here we start at 0. So we can't apply it just yet. So instead, we have to rewrite this summation a bit. So we can say that this over here, let's copy that, paste it. This integral right over here is just equal to the integral from 0 to 1, n e to the minus epsilon n dn, plus the integral from 1 to infinity, n e to the minus epsilon n dn. Because an integral is just an area, right? So we can just add these areas together. So this means that this entire thing is just the summation from n equals 1, n e to the minus epsilon n, minus this entire thing right over here. So that's just the summation from n equals 1. So we can actually explicitly integrate this middle term right over here. So the integral from 0 to 1, n e to the minus epsilon n dn. If we were to take the limit as epsilon approaches 0, which we have right over here, remember that? So we can just like move that inside, right? So the limit as epsilon approaches 0, we're going to have just n right over here. And we know what the integral of n is going to be, right? It's going to be equal to, you know, that's a very, very good question. That is going to be equal to, I almost forgot to integrate n, I'm sorry, n squared over 2 from 0 to 1, and that's just going to give us 1/2. Yay. So now this term is going to be 1/2. So we're going to now have, and that's going to be what's on the inside, by the way. That's on the inside. So just like keep that in mind here. So now we can apply the Euler summation formula to this term right over here. Okay, so let's just copy that and paste it again. Copy, paste. So yeah, we have that. And now we can see that these bounds are the same. They're both 1. So what is, oops, let's redo. So what is f? Okay, so remember, let's just ignore the minus 1/2 right now, by the way. Let's ignore that for now. So what is the f here? Well, the f is going to be the n e to the minus epsilon n. So the first step, let's break this down into steps so that we don't like go crazy. The first step is you want to find out f of a plus f of b over 2. Here, a is just 1 and b is basically infinity. Or better said, the limit as like x approaches infinity or whatnot of x. So f of a plus f of b. Well, f of a, that's just going to be a is 1, right? So f of a plus f of b, that's just going to be f of 1 plus f of infinity, then over 2. So what's f of 1? That's just going to be 1 times e to the minus epsilon times 1, and then plus infinity, this is going to look very weird, e to the minus epsilon times infinity over 2. Now, you guys might be worried about this second expression right over here, which is why we should really say the limit as n approaches infinity of n e to the minus epsilon n, because it turns out the exponential is a common rule in math. The exponential will always win. So this exponential is going to go to 0 faster than this term is going to go to infinity, basically. So this term over here is just going to be 0. And when we take that limit as epsilon approaches 0 over here, that's just going to make this become 1. So for our first term, we just have 1/2. Pretty simple, right? And we're going to repeat this the same step for 2. So for 2, we want to find f prime of b minus f prime of a over 12. Let's move this a bit down over here. So that's just, again, going to be f prime of infinity minus f prime of 1. So what's f prime of infinity? Well, what's f prime to start with? Well, if f is f of n, really, it's going to be n e to minus epsilon n, and d over dn with n e to minus epsilon n, it's just going to be product rule. That's going to give us e to the minus epsilon n, and then minus epsilon n squared, I think. Yeah, n squared e to the minus epsilon n. No, just there's no n squared, just n. So this term over here, we can ignore it because when we take the limit as epsilon approaches 0, this term is just going to go out to being 0, right? Not the limit as n approaches 0, the limit as epsilon approaches 0. So this term is just going to be 0 right over there, right over here. And that's because this term is going to be 1, and this term is just going to be 0. So 0 times 1 is 0. So we can just really just focus on this term right over here. So we can again do the same thing here. We have e to minus epsilon times infinity, or then minus e to minus epsilon over 12. This is going to go to 0. This is going to go, like, yeah, that's going to be 0. This one over here, when we take the limit as epsilon approaches 0, this term goes to being 1. So we get minus 1 over 12 for the second term right over there. So the second term just gives us minus 1 over 12. Now what's about the third term? So for the third term, it's going to be a bit more complicated. You have to take the third derivative. So if the second derivative was, I forgot what the second derivative was. Now I have to do it again. Well, that second derivative is going to e to minus epsilon n, and then plus minus epsilon n e to the minus epsilon n. For the third derivative, that's just going to be minus epsilon e to minus epsilon n minus blah blah blah. You guys can figure it out. And the third derivative doesn't matter, right? Because when we take the limit as epsilon approaches 0, we have that epsilon in front, right? So this is just going to be 0. So the third term is just going to be 0. So yeah, the third term is 0. Now if the third term is 0, right, the fourth term is also going to be 0. Since the derivative of that, we're just going to have more epsilons in front, right? We're going to have epsilon squared e to minus epsilon n plus dot dot dot. And all the higher order derivatives are also going to be 0. So really we just have to stop at the second term right over here. We don't have to actually care about the higher terms. So basically what we found out here is that the sum over here, this sum is just going to be equal to 1/2 plus, or just really minus, 1 over 12. Pretty neat, isn't it? So let's go all the way back here. Where are we going back? Let me see if I can. Yeah. Let's go all the way back here. Remember that there was actually a 1/2, minus 1/2 here, right? So we found out that what's on the inside is 1/2 minus 1 over 12. Now, to make our lives easier, let's write these in terms of a common denominator. That's just 6 over 12 minus 1 over 12, right? And that's just going to be 5 over 12. So on the inside, right over here, we have 5 over 12. So 5 over 12 minus 1/2, that's just 5 over 12 minus 6 over 12, which is just going to be minus 1 over 12. Pretty cool, isn't it? So we have minus 1 over 12. So we're almost done here. Stay with me. This entire thing is just going to be minus 1 over 12, which means that this entire thing over here is going to be minus 1 over 12, which means that this entire thing here is going to be minus pi over 12a. Yay! We've got our answer for delta E. We're done. That's that's it, right? I find it remarkable how, like, in the Casimir effect, it starts off pretty straightforward, right? And then it kind of gets complicated, but it's in a more elegant way. It's kind of weird. It gets complicated, but because it's complicated, it becomes simpler. Because before we had that delta E was infinity, but now we just found that it's a finite term. And what we've done here is called regularization. You guys will hear this word a lot in your QFT course. It's a very important concept. All it means is that we take expressions that are divergent and we make them finite through a series of arguments. So the regularization that we used was the one called the Euler-Maclaurin formula regularization. And basically what we've done is we just said that, oh, some photons can contribute, and using that reasoning, we made an infinite term, a divergent term, now converge to a finite amount. So since the change in the energy is just going to be minus pi over 12a, let's go all the way back to our plates. Let's kind of erase some of these things. The change in the energy is going to be minus pi over 12a. What's the force going to be? Well, the formula for force in this scenario, let's use green, it's going to be the negative of the partial derivative of the energy with respect to A. So minus partial of delta E. Oops, wrong one. Partial of delta E over partial A, right? And delta E is just going to be what we found, which is minus pi over 12a. So what's the derivative of minus pi over 12a? Well, that's a very great question. The derivative of that is going to be minus pi over 12a squared. And this becomes a positive. So now you have minus pi over 12a squared. The answer is minus pi over 12a squared. I should probably write that really big so that be sure that that's our answer. So there is a force of minus pi over 12a squared. So that is an attractive force because we have a negative sign, which means that these plates will actually exert a force towards each other, their strength being pi over 12a squared. So the further apart these guys are, because a is really just the length of the distance of the plates, right? So the further apart these guys are, the smaller the force is going to be. The closer they are, the closer the force gets, or the stronger the force. So yeah, that's the formula for the Casimir force. This is what we were trying to find, and we got it. So that's how the Casimir effect works. Basically, what we've done here is first of all, we had the Hamiltonian. We found the energies inside of the plates and outside of the plates. We subtracted them together. We found out that we get infinity. Then we used a regularization where some photons escape the plates, or some field modes escape the plates, and that made our expressions finite. And from that, we found out the change in energy is minus pi over 12a. We took the derivative of that with respect to a, took a negative sign, and then we got the Casimir, the main Casimir force. So yeah, that's how the Casimir effect works. Now for the subtleties. The Casimir effect in its current state is a very controversial effect. The effect the effect itself isn't controversial, but the explanations of the effect are controversial. Because we've actually used vacuum energy here, right? Because remember how before in quantum field theory we were like, oh, we get we get an infinite term here, right? We just pretend that it doesn't exist. We just remove it, and we have a modified Hamiltonian. Well, through the Casimir effect, we were actually using this 0 point energy. So the Casimir effect, since it's derived from that 0 point energy, it kind of implies that 0 point energy is a real thing, right? It's a real measurable thing. But some physicists say not so fast, because the Casimir effect can actually be looked at from a more, material lens, as simply the product of a van der Waals force. Because if you actually look at the formula for a van der Waals force, you'll actually find out that the van der Waals, how do you spell van der Waals? However you spell it, is proportional to 1 or minus 1 over a squared. So the van der Waals force between two conducting plates is actually very similar to the Casimir force. In fact, one could actually argue them to be the same thing. So you can actually derive the Casimir effect by just using the van der Waals force between the plates uh, instead of talking about vacuum energy at all. So you can derive it for the case where there's zero vacuum energy, and you get the same thing. So there's this debate about whether the Casimir effect is actually due to the vacuum energy, or if it's just a van der Waals force between these two plates. Because remember, these are real, like these are supposed to be plates with atoms in it and stuff. And atoms, like a van der Waals force, for those that don't know, is it's a force that results from the like distribution of charge in a system, it but being uneven. So we have an uneven distribution of charge in a system. Think about the London dispersion forces, right? Where we have like a hydrogen atom, right? We have a proton and an electron. They have two hydrogen atoms, right? And if like the electrons of these hydrogen atoms just so happen actually to be fairly close to each other, just so happens to be the case, they might actually attract for a brief amount of time. And that's a van der Waals force. So it results from the fact that charges aren't always evenly, or most of the time are slightly unevenly distributed. All right, and this kind of makes more sense where we have entire molecules, right? So we can derive the Casimir effect by treating it as a van der Waals force. So there's this whole like kind of debate, and I encourage you guys to actually look into this debate. There's even a debate about whether the Euler-Maclaurin series or formula even makes sense to use in this context. There's a lot of arguments out there, and I highly encourage you guys to look at them. But it's nice to just know how to calculate it yourself to like better understand these arguments. So with that said, that is how we derive the Casimir force. I hope you guys enjoy this video. If you like it, consider subscribing or perhaps sharing with your friends. And yeah, thanks for watching and have a great day. Bye.